All right, welcome everyone to our second session of our PacTrans event. My name is Carrie Sturtz-Dosick. I'm faculty in the Department of Construction Management in the College Built Environments. I also serve as the Associate Dean for Research there. And I'm really excited to participate in this conference and help host the cybersecurity session this morning and now our session on digital twins. Is the audio okay? It sounds a little echoey up here. We okay? Okay, great. So I'm excited to bring a really interesting panel to the discussion today. Digital twins are definitely an emerging term, an emerging space. We're all in the industry, in private sector, public sector, academia, all kind of getting our heads around what these things are, what we're doing with them, what they mean. And we're gonna explore a bit of that today in our discussion. We have lots of examples to talk about. I'm excited to introduce my panelists. I'm going to kick it off myself, and then we'll bring up each panelist in turn for about 10-minute presentation, and then have time for discussion. So Raymond Kay is joining us. He's an assistant professor of civil and environmental engineering from Rensselaer Polytechnic Institute, and is going to be bringing some examples of digital twins with him today. Nargis Abbas Abdi, I had it a minute ago. Abbas Abedi is an assistant professor in architecture in the University of Washington, and I welcome her as a good colleague of mine, going to share some citywide digital twins examples with us. And finally, Esther Chitsende is joining us from the private sector, is a senior environmental planner with HDR, and brings some exciting examples from her work in Texas, particularly at the Dallas airport. So, not further ado, we're going to turn our slides on and get started into our content. Presentation mode. So I get to kick us off and do an introductory remarks related to defining these concepts of smart buildings, smart cities, and digital twins. I've covered a little bit about myself, who I am. I've been looking at technology and design, construction, and operations for over 2 decades, starting in the process and power sector, going into buildings, and now in transportation. So I'm seeing that digital twins are a new term for some technologies that have been in the industry for quite a while, but we're adding and integrating new technologies in new ways in this digital twin space. So some of the technologies are new, some of the technologies are a rebranding of some things that we've been using for quite some time. So where does the digital twin term come from? It was coined by Michael Greaves in the University of Michigan around 2003, defined as a digital equivalent of a physical product. And it was really coined in the context of NASA and the missions to Mars, thinking about if we're sending these robots to Mars, how do we control and understand them and simulate them here on Earth? So they had a physical twin of the Mars rover here on Earth. They also had virtual twins of this rover. So the idea of twinning emerged out of NASA, but has proliferated all throughout lots of sectors. So NASA's digital twin is multi-physics, multi-scale, probabilistic simulation of an as-built vehicle. So there's this idea of being able to simulate something in the future, or even simulate something that you don't have physical contact with, and understanding performance from a remote physical location. So there's ideas of sensors, ideas of mirroring, something that's happening in its corresponding flying twin. So we're seeing these kinds of technologies used in manufacturing and transportation, city-level governance, pharmaceutical industry, healthcare, medical system, legal. Like many technology hype terms, this is like taking off in lots of places. People are super excited to talk about digital twins in a lot of industries. So in my lab here, we've been studying digital twins for the last couple of years, and I did an assessment of what characterizes digital twins in the built environment context. So I'm going to kind of bring us into our built environment context now. There's different characteristics that we've kind of accumulated to define digital twins from this research. And these include real-time reflection. We're getting real-time information from the environment that we're able to process, analyze, and understand through a digital twin platform. There's life cycle reflection, so we're able to put that real-time information in the context of historical performance and predicting future performance. So thinking about how this fits into understanding the life cycle of the object or product that we're twinning. There's some sense of autonomy. We're able to use the knowledge and maybe even automate some of the systems without human interaction. So, for example, if these shading devices were reacting to the sunlight, they would go up and down without us pushing the button to go up and down because they were ready to let the sunlight in if it gets cloudy and we're able to we want more daylight coming in. It helps us get clarity. There's value generation, ideas of evolution, so our systems can change and learn over time. We're going to hear probably a little bit about that in the AI work that we hear about today. An idea of openness, the democratic nature of data. Do we allow some of these data to be more accessible to the general public and helping them make decisions? Some of the buildings on campus, you might see some panels in the front of the building where you can go up and understand the rainwater consumption or energy consumption of the building, being able to allow people to see and understand how their building or their infrastructure is being impacted. So these are some of the attributes you're going to find in the digital twin systems that are coming out. Where we found this out was from a survey. We had 108 international respondents from all over the world that included our technology developers of these digital twin systems, the technology users, and in some cases they were both the makers of and users of digital twins. Coming from multiple continents of North America, Europe, and Central and West Asia. So this is an eye chart, not meant to be read in great detail, but what I wanted to impart with you is that there's a lot of different technologies being integrated in digital twin systems. So if you think of an information technology, somebody's probably using it in a digital twin. So it's 2D, 3D representation, it's VR, it's data, it's AI, it's machine learning, it's 4D, it's data mining. It's all the things that people are exploring particularly with data, people are using in some sort of digital twin platform. And it's in different combinations of those platforms. So you can see the bars there are representing, sometimes it's not applicable, sometimes it's included, and no single technology is always present. So various digital twins have different constellations of technology. That's the takeaway from this slide. And we're going to see some really great examples today. So when we think about digital twins in our buildings and cities, we're seeing these applications being used in the design phase, thinking about simulations, thinking about designing, perhaps analyzing existing facilities and infrastructure, analyzing performance of designed objects, simulating future performance. Okay, designers, we've been doing that for a long time, right? So this is adding capabilities to our existing analysis systems. In the manufacturing phase, there's real-time monitoring of production, production control, and production planning applications. And then in the service phase, we're predicting maintenance, default detection, state monitoring for service phase could include construction as well as operations. So we're seeing a lot of interesting exploration, and I'm happy to hand it over to my colleagues to show some specific examples. So I want to invite Raymond Kay up to present his work in this space.
Good morning, everyone. Thanks, Carrie, for the nice introduction of the overall digital twin concept. And I'm going to give an example on the how to build a digital twin for a campus digital twin model at the University of Texas, El Paso, even though right now I'm at RPI, Rensselaer Polytechnic Institute. I just joined this semester. During the previous 2 years, I was at University of Texas, El Paso, UTEP, where I led a project sponsored by the C2 Smart UTC on building a campus digital twin to study the interaction between transportation system and infrastructure. So I would like to acknowledge the sponsor from C2 Smart Center and also PacTrans on the invitation on the trip and organizing this amazing event, and also the sponsor from UTEP, like the UTEP facility and RPI. So I also had a few slides of what's a digital twin. I will quickly go through, for example, digital twin, a few key components Carrie already mentioned. It's a digital replica of a physical entity or system, and usually integrates real-time data and simulations, and there's two-way communication between the physical twin and digital twin, and used to analyze, simulate, and predict the real-world scenarios depending on the use cases. So you may have different functions, integrate different components and technologies to build this digital twin. And there's definitely benefits of using digital twin, for example, efficiency, accuracy, safety, innovation. I'm not going to go through all of that since Carrie already mentioned this. And in transportation, we see like transportation twin, like connected vehicle, digital twin for studying, for example, RAM metering, signal control, vehicle maintenance, public transit, or for example, transportation planning if we want to build a new road or reconstruct a region. So what would happen to the congestion, safety, what's the benefit and cost? And if we have a digital twin, we can see the what ifs and playing with the different configurations. That would be the benefit to the analysis, safety analysis. What if there's a crash, and so how much the cost and the delay, and so how much resources we would need to like deal with those situations. Introduction to the specific this project, we explored the digital twin as a tool to manage like the campus, like traffic network and civil infrastructures. We call this digital twin a Smart Living Lab, or SLL. At the beginning, we had a name called a Small Lab, but later we found that SL might be a little bit better name. So you can see from the figure, that's like a campus map, and we try to instrument different sensors, and with the real-time information and communicating with the server on campus to collect the campus infrastructure and traffic data. And we actually had 3 sites in this project. I will introduce one of them, which is the roundabout at the garage at the UTEP campus. And there were two co-PIs leading the, so focus more on the pedestrian bridge and using LiDAR scanners to build a digital like twin for the building. So quickly go through the tasks and goals of the project. It's kind of regular. We had literature review, we had built a digital model of the campus using different sensors technologies, and we did some experiment on like which sites to be selected in the project and to study the digital model and digital twin, and then implementing the Smart Living Lab and digital model integration with the sensors and digital model, and then with the simulation, the digital model we built to conducted some scenario analysis on how the digital twin can be leveraged to help us. And also we conducted in the project outreach workshop at the local, so we engaged the local, like the city, the DOT people, and the airport people, and to disseminate our project outcomes. And there were a few challenges definitely in creating digital models. This is more of a, so as Carrie mentioned, there's a lot of existing technologies. We are rebranding these technologies, but digital twin is more of an integrated concept depending on the use cases. And in our case, the project, we mentioned a few challenges. For example, the road networks can be simulated from GIS data, but only in 2D from OpenStreetMap. And we could use aerial LiDAR data to create the 3D terrain and buildings, but it's slow and costly. And in the CARLA simulator, which is autonomous vehicle simulator, we could manually label the 3D, use manual 3D modeling for the autonomous vehicle research. And there's definitely enterprise services provided, for example, by Microsoft, AWS IoT, and Bentley iTwin, to support different types of digital twin applications. And there seems to be no simple and open source solution for university campus digital models. And also, when we are trying to build let's say, a campus digital model, the road network information may not be as complete as, for example, on an interstate highway. So if we directly use the OSM, OpenStreetMap information for university campus, it's usually incomplete and out of date. For example, there are two roads, they are actually connected, but on the OpenStreetMap, there are no connection between them. So you cannot directly use those information. And the building information and 3D CAD models, they are generally not available, and no single software, especially open source software, to create these models quickly. And there are a few challenges. And to address these challenges, this project, we focused on using all open source like data and information and software to create a campus digital twin. For example, the data from OpenStreetMap, Google Map, and Mapbox, and different softwares like the Roadrunner, Unreal Engine for creating simulation, and the terrain information, building information, how to integrate this information. And we actually have a step-by-step tutorial on the City2Smart website. There's a student learning hub. The video is still there. The presentation was given by my PhD student, Taha Asfa, who's now at RPI as well. So we mentioned a few softwares like the RenderDoc. It's a graphics debugging tool that can extract the 3D data, like terrain buildings from Google Maps. I mean, of course, those data are not as detailed, high resolution as, for example, you use a LiDAR scanner, right? But that's from open source, and the 3D meshes can be imported into Blender using the different plugins. And the trees, parking lots, and even parked cars can be visualized and studied. These are a few screenshots like during the digital twin model creation. You can see, for example, this one is how we integrate the routable road traffic network. So you can think of the roadway have a different layer, and how we combine them into the 3D, like terrain buildings, trees, parks, extracted from the software. And the last two, the ENF, those are we visualize the product we created. This is University of Texas El Paso campus. And we mentioned this CARLA project, right? It's an open source autonomous driving simulator and use Unreal Engine. And here we integrated, merged those information into the CARLA. And you can actually play with it, and it's like playing a game. We created, there's some agent, it's like a robot, and you can actually navigate the campus, the digital twin we created here. And it composed of about 1.59 million triangles, and we did this work on it's a quite powerful computer desktop. This is from the CARLA, like Unreal Engine. So you can see this is like we created it's like a car agent. It can navigate through the campus, and we can extract, from the cars, the driver's angle, the different sensor data, for example, the LiDAR data, the depth information from the car. And the last picture was a sumo like simulator. We create this, it's like a co-simulation in both the 3D and the Carla and also the sumo to simulate, in this case, the campus roundabout and traffic. For digital twin, in addition to a digital model, right, we're going to have the real-time integration of the data. And in that case, we use the NVIDIA, the IoT computer, Jetson, and the camera to apply some AI-based vehicle detection tracking technologies and to interact with the digital model we created. We mounted this on the garage and to apply some vehicle detections based on the NVIDIA Jetson. And then the information is transmitted back to the server, the computer we have. In this case, is actually the desktop and it's a workstation we have here. And this is a screenshot from the camera, the video we labeled a few, those green regions and these areas is where we actually count the number of cars. And you can see those cars, we developed these like detection and tracking like in the camera videos. And in that case, we have the roundabout, and the traffic enter and leave their trajectories, the vehicle trajectories as well, and the volume, the count. And then another step is to align the coordinate systems, right? Because we have this real world video detection, the camera coordinate. We also have this in the Carla, the virtual, the digital roundabout. So you're gonna, if you wanna, let's say, project the cars, the traffic onto the digital model, you're gonna do the calibration, right? So you know that this is a car, it's the same car at this place in the real world, and it's at this place in the digital model. So this is a little like a GIF when we show like the traffic, the cars, can see how it's projected. Even though the direction of the cars, due to the limitation of software, it may not look very real, but the location is with the calibration, we can project the cars into the digital twin. And we can, in the scenario analysis, during that time, we had a construction zone near campus, near the roundabout. Actually, the 4-lane roadway was cut into 2-lane, and we did simulation. And so in the digital twin we had here, this is in the sumo, right? And we quantify the delays, the impact of the construction on the sumo and Carla co-simulation. And here you can see the visualize this is a 3D in Carla, and that's in the sumo with 4 lanes and 2 lanes. And here on the top, this is basically a screenshot. It's like a figure showing the trajectories of the cars, and this is from the surveillance camera's angle. And we have a few papers and presentations made out of this project. We also had this tutorial and another introduction video on YouTube on the whole project. Most of them are released earlier this year. So that's about my presentation, and thank you very much.
Thank you. I appreciated the diagram of all the different software being integrated. I think that's a major theme of the digital twin space, as we're seeing the integration of multiple technologies, multiple visualization technologies. So I'm going to welcome the next speaker, Narjis Abbas Abadi, to present another example for us.
Hi, everyone. It's such a pleasure to be here. Thanks, Gary, for the introduction. My name is Narges Abbasabadi. I'm an assistant professor of architecture in the College of Built Environments at UW. And today I'm going to talk about hybrid twins, scaling up digital twin for city-wide building energy management and modeling. And a little bit about my research background. My research focuses on computation within the built environment. And much of my work has focused on developing methods, frameworks, and tools for better understanding energy flows within the built environment and advancing decarbonization, specifically using machine learning and physics-based simulations. Climate change is a critical issue, and statistics are very wide public knowledge. Cities are responsible for a significant amount of energy consumption and associated emissions, and buildings play a big role, 40% of global energy consumption. Cities need, or many of them have committed to reduce their energy consumption, and it needs to happen at a scale, and buildings offer significant potential for that carbon reduction. At the same time, we're living in a very interesting moment in time. We are living in the age of growing, emerging digital technologies, open data initiative, and infinite computing or multi-sensing technologies that influenced our cities and have increased our ability to better understand the interconnected problems within the built environment. So from mobility to energy, human health and well-being, bringing human into the feedback loop, and potentially enabling the cities to be a stage of transformation. Digital twin, as my colleagues discussed it very well, it's a new emerging digital concept that can or has the potential to facilitate accelerating data-driven studies. And to conceptualize urban building digital twin, first we need to differentiate between DT concept and some other closely related technologies, specifically around modeling that can be building information modeling, city information modeling, or city 3D models, and urban building energy models. So a model is an approximation of the real world, and simulations are repeated observations of that model that allow analysis and visualization of the behavior in a specific condition. And it can go across a scale. It can be an architectural element, a room, a zone, a building, or a neighborhood or a city. But a digital twin, so the main difference here is that virtual replica of the real world that is dynamically fueled by real-time data. And this creates a feedback loop between the physical twin and the digital twin. And when we are talking about that live interconnection, really at a larger urban scale, it doesn't mean instant streaming data or instant interventions. But the idea is that constantly being fed by real-world data. These data at urban scale now are huge. So from physical sensors, from remote sensing, from process data such as spatiotemporal studies that generate data, as well as geotag data such as social media data, mobile, GPS, and other sources. So in terms of evolution, we can say that at the basic level is a model which there is no connection between them. And then at the second level, one-way direction, and more recent developments include bidirectional communication that kind of enables that self-corrective action. Gaining or more future goals is that how to make that more interconnection, multifaceted digital twins, and a city digital twin can encompasses many sub-DTs, for example, here with the building digital twins. And in terms of applications, for the sake of time, I'm going to just quickly pass it. So with the demand side for energy efficiency, demand forecasting, fault detection diagnostics, and then for the supply side for kind of response and grid interaction. But the main question or argument here is that where we are at the stage, so the application of digital twin for the building case is limited to the individual building scale. And what we have at larger, so few campuses, few case studies, we can find that they have that smart infrastructure. So the problem is the novelty of the technology and the lack of that widespread smart infrastructure doesn't allow us to build a digital twin of a city to kind of, for that energy case to kind of explore some intervention scenarios. Here the argument is that the convergence of digital twin, big data, and data-driven techniques such as machine learning and urban building energy modeling can provide us some promising opportunities to fill those gaps. So urban building energy modeling that can generate that essential information in the case when we don't have access to smart infrastructure or collecting data. That can can be categorized into two major groups: physics-based modeling and data-driven. So physics-based relies on fundamental laws and equations from physics to predict the behavior of that system, and it's mostly based on using software engine to do it. And then the data-driven relies more on predictive information modeling using machine learning. Here is an example for Chicago that we have developed a model, a predictive and explanatory model, which has been published in Applied Energy. So I'm not going to discuss this more. So it was mainly for kind of gaining insight on how various elements influence energy consumption in a city and how we can do some interventions, and specifically generating information that are missing here. Each of these methods have their own limitations. That physics-based engineering simulation has uncertainty since it relies on some archetypes, for example, at a larger scale. And data-driven one relies mostly on availability of data. So here we, in a new ongoing project that we've just started, so we're trying to bridge that gap with linking digital twin data to data-driven and physics-based simulations to make the models more accurate and efficient, and then change that static environment of urban building energy modeling to more dynamic, enabled ones. So here we're exploring with the University of Washington's campus. We gain access to the building to the data from some of the buildings. Here we're exploring time series analysis to identify inefficiencies, and then the most importantly, we're going to make a framework of how we can bridge the gap between that physics-based simulation and data-driven one, and generate synthetic data when we don't have access to real data. And another one, we're going to augment such model with other aspects of when we're talking about energy within the built environment. So equity and health aspects, some specific strategies when we're using for energy reduction, they may put people at health risks, such as not considering air pollution or air quality condition. A relevant recent project that has been for Chicago and we published it in Sustainable Cities and Society. So here we're looking at the intersection of energy, air quality, and health and equity aspects. And more close kind of with what-if scenario analysis in this area. So just to summarize my presentation, we believe with a hybrid approach at larger scales when we don't have access, still we are not at that stage because of the novelty of the technology and lack of widespread smart infrastructure, how we can hybridize that simulation physics-based modeling for generating synthetic data, and how some other big data sources, such as when we're talking about social media data, which is near real-time data sources, can inform some of the aspects, such as energy consumption in buildings or occupancy patterns in building. Thank you.
All right, you can see I've challenged them to squeeze their projects into 10 minutes, and they're doing beautifully. So fasten your seatbelts. We have another great talk to unpack with Esther Chitsende coming in from Dallas.
All right. So you've heard from Roman, you've heard from Nargis, and you've heard from Carrie. And I'll just give you some examples of what we've done during my time at DFW Airport, as well as what is being done at HDR, and then what's being done in the industry in terms of the power that we're seeing from leveraging digital twin technology and how it adds to our toolbox. And it gives us another tool that contextualizes all this information and helps us make better decisions. And as an environmental scientist, it also helps us address the problems that Nargis had brought up in terms of climate change, because that is a complex problem requiring us to approach it from different perspectives. So I'll start with HDR's role in the space of digital twins, and right now our role is providing digital transformation strategy and helping clients with roadmaps, as well as providing digital advisory services, digital delivery services, so that as this process of digital twinning evolves, we're empowering different people and different clients, different industries, and helping them evolve with the journey and with the technology. We also have a data acquisition and data delivery team. So I will just jump into a brief why digital twins spiel, and we can use them in planning, like Carrie said, design, construction. We can have operational twins, and I'll give you some examples, or an example of an energy optimization digital twin and how that has led to energy cost savings. And then you can use it to enhance maintenance and asset management, and also support continuous commissioning. You can also leverage digital twins in terms of sustainability and resiliency, going to what Roman said in terms of running what-if scenarios and contextualizing information, and then starting to understand how the different scenarios you're dealing with, or different circumstances, disruptions, what could you do and how does that influence or impact the system? So in terms of how are digital twins enabling sustainability and holistic decision-making, to me, it starts with me defining what does sustainability mean to me. And it means me using resources in a responsible manner so that I don't compromise or strip the abilities of future generations to live, thrive, and meet their own needs. So I see digital twins as a way that contextualize that data. Data is coming from different sources, and I'll give you an example of an airport ecosystem. And just jumping into airport ecosystem, an energy management system at HDR, and then a dam that was modeled and leveraging the same digital twin technology, just to show you the breadth of opportunities to use this technology and leveraging it to do better for our shared environment that we live in. So HDR has built the energy management digital twin. This is actually for our headquarters. And then we've also built one for the Diablo Dam that's local. And then we also worked with DFW Airport. I worked with DFW Airport on a mobility digital twin, and that was funded through the Department of Energy, and we worked with the National Renewable Energy Lab as the team of researchers enabling this work. We also worked with NREL for the Morpheus Energy Optimization Digital Twin, and then I'm also going to showcase what NREL has done for their own campus with their ESIF Building Operations Twin. So for HDR, the idea is, our focus is to understand how this technology can empower others. We need to bring it home. We need to exercise what are we trying to understand. And we had just embarked on a journey of designing a new headquarters building. And so HDR has 12,000 employees globally, but we're employee owners. So we wanted to know, what are we trying to market and what does it mean? And so with the headquarters building, the use case was mostly focused on taking the sensor technology that we had already decided we're integrating and then designing the building and incorporating BIM because we had already decided on that path, but now starting to move into, it's a LEED Gold building, and we're also trying to get well certified, and how do we monitor performance of those aspects of the building? And so that's how the digital twin for the HDR building, that's how the decision was made. And we've been able to visualize in terms of how the building is performing, air quality within the building, space comfort, and we've been able to use research to correlate that the importance of good indoor air quality as well as space comfort. What does that do in terms of translate to value, in terms of employee comfort, productivity, and then the business imperative or the business outcomes for our company. In terms of the Diablo Dam, HDR was hired to build a digital twin and help with inspections, and we had captured drone footage, and then we also captured point cloud data, which is a lot of data. Like Narjis was saying, we're also living in this world of big data, but the idea was find ways to reduce costs of inspections, find ways to improve safety, and how can you leverage technology to address those issues. And we were able to build this 3D model of the Diablo Dam and then build a twin, and now we can run what-if scenarios in that twin to understand what are areas where there's maybe stress and how could we address those issues before they happen. And then I'm going to move into the airport environment, another example of a digital twin, and we'll start with airports as complex ecosystems, and this is just showing how airports are interconnected, and you could replace airports with this university campus, the organizations we work with, the cities, the counties, and it's just telling you that the system is interconnected and interdependent, and there's other systems that are related to what we do, and we depend on each other to fully succeed. And in addition to that dependency, there's also external stressors that range from environmental stressors and climate change, and then regulations. So this is just trying to help you understand the dynamic nature, as well as the fact that we have to think of everything as a system because we're all interdependent. And airports are seen as that one of those complex ecosystems, and DFW is a great example. And at DFW, once we realize that we're system dependent on other systems and we really function like a natural ecosystem. I'm an environmental scientist, so that frame of mind makes sense to me, and framing issues in that concept truly resonated. And so when we talk to DFW leadership, and when I was there, it was starting with the digital transformation strategy, trying to understand customers because they're part of that system, trying to understand the telecommunications information, and then trying to leverage strategic partnerships because we recognize that we don't have all the skill sets. So partner with, people from the Department of Energy, partner with people at universities, partner with the National Renewable Energy Lab, the experts that are in the field that are going through, and even partner with industry and other technology providers who are trying to run and test these different technologies that are evolving. So DFW came up with the Athena Mobility Twin and the Morpheus Twin, and this is just a graphic showing you that Athena was incorporating different data sources, and the idea, like Carrie said, it's democratizing the data. So take data from multiple sources that usually sometimes don't even communicate, so sometimes you don't know what your counterparts are communicating, but the digital twin helps you take the different data streams, put them in one platform so that you can share, so that I can make my decisions and I'm informed and I understand the unintended consequences of something I'm trying to do. Say I come in and say, you know what, let's shut down all operations because we don't want to pollute air. What does that mean for the airlines? What does that mean for the finance team? How do we make money? What does that mean for the passengers? And I'm a passenger too. So this gives you a snapshot or a perspective into, we need to bring the different data and democratize it so that everyone gets access to it, and then move into starting to make decisions, running what-if scenarios. And then in terms of the Athena example, one of the ways they used it was running a planning simulation of an emergency situation that led to a road closure, and then trying to understand if this happens and you don't implement a policy, run it in the digital twin, you notice that there's congestion and all the red is telling you that roadways are getting congestion. So in the virtual environment, you start running some potential solutions and evaluate thousands of solutions and start rating them in terms of which ones are most effective. And so with the policy, you start realizing that, oh, we could implement policies in the virtual environment, and this is what it would translate to. And then you go validate it in the field with a mock, I guess, trial to see how the system actually behaves. And you do it over and over again with multiple situations. They all ended up using the digital twin to also run a similar scenario with a roadway closure. And then they decided, okay, we've learned through the mobility digital twin, let's try this by building an actual digital twin for a building, and this was focused on the Terminal D facility, which was mostly proof of concept, also a partnership with NREL, Oak Ridge, and the Department of Energy. And the idea is get a 3D model of the terminal and then start understanding how is the terminal consuming energy. And this became a very important issue during COVID because we noticed that space utilization had dropped to almost less than 10% because no one was flying. But energy costs were going up because we didn't have a dynamic way to manage energy systems. And with a digital twin that consolidates the different data sources, now you know that when a space is not utilized, you shouldn't be running your HVAC, you shouldn't be running your lighting systems, and now you can even used the technology to push out a solution so that it's not just on a schedule, but it's now actively responding to the demand in the building. And this also has implications in the central utility plant and allows us to, and we built a digital twin for the central utility plant, and we're able to dynamically manage thermal energy storage as well as the chillers, how they operate, to make sure we're optimizing comfort, but also reducing energy costs. And they noticed that with the Morpheus digital twin, energy costs were lower, energy consumption was lower by between 10 and 16%, which translates to over $200,000 in energy savings a year. And then NREL, this is just an example of data visualization for their digital twin, focused on understanding what is happening in the building, which areas need more HVAC or need you to turn the air on, and which areas are not being optimized for comfort. And so this is, again, a picture telling you a story of what the power of a digital twin can do, because right now you already understand that, oh, there's some parts that are not doing well in the building. So I'll leave you with this statement, and this is a question that we can go down rabbit trails and discuss. What do we owe the future? As Nargis said, climate change is confronting us. What tools can we take on together? How can we address these problems? How can we leverage this technology to address sustainability and to report and be transparent, like Roman said, and provide this data and share it so that we can have a better, brighter future for all of us? And then in terms of who made this possible, in addition to HDR, DFW, NREL, Oak Ridge, and the Department of Energy supported this work and have graciously made it possible.
Thank you. All right, warning, I'm going to turn the lights on, so prepare for a visual change here, because we get to open it up for questions. So we have some really exciting examples, beautiful visuals of integration of digital data and digitization of our built environment. So we're open for questions.
Hey, thank you. Those were great presentations. Has there been any work done on EV charging stations in terms of, where would they go as the adoption of EVs is increasing?
Has anyone on the panel worked on EV?
So I can take an attempt to answer your question. That's actually currently happening at DFW. They just launched a project, another partnership project with the National Renewable Energy Lab, and it's called Athena ZEV, and they've deployed some EV charging because the cars are here, they need to use the charging systems, but trying to understand how do EVs influence or impact the grid. So they launched this project about maybe a month and a half ago, and it's focused on partnering with rental car companies, and Hertz is one of the largest partners because they are trying to change their fleet. And so we're trying to understand how does that fleet transition affect the energy grid, and can we have distributed energy resources within the airport environment so that the impact of EV charging, because they'll plug in when they need to plug in, but we cannot compromise the rest of the system. And they're going to be testing those scenarios in the digital twin environment before they start deploying massive, charging infrastructure.
Great, thank you. I'll also plug for an afternoon session. We're going to be talking about EVs after lunch in one of the sessions, so I'll direct you to that session as well. Great.
Talking about energy consumption and climate change, all these technologies we can speak about in terms of helping energy consumption and climate change. But the more we use those technologies, especially as we go into AI, they themselves have impacts on energy and climate change, which sometimes are not spoken about so much, but especially AI can have a huge impact on climate, and also the cost and resources that may be required for this. I was wondering if you, Esther, could comment on that.
Thank you. I'll attempt to it, and then I'll throw it over to Nargis. So in terms of energy consumption, that's one of the biggest concerns, right? And that takes you back into that systems thinking. We have to leverage the tools that are available to us now, but we always have to continuously evolve and learn, because to your point, AI, we could leverage it for the better, but we could also have unintended consequences if we work in a vacuum. And the same applies to the fact that all this data we're collecting goes into some place, and that place consumes a lot of energy. And if we think of it in a vacuum, we'll end up in just a different part of the problem. So the part that gets me, I don't have a good answer for you, but the part that gets me excited is the fact that we're thinking about it, and it's not a surprise, and now we're actively having the conversation and brainstorming. And as we brainstorm, we'll keep finding problems, but we have brilliant minds coming to a conference like this one and saying, hey, these are the solutions we're seeing, these are the opportunities, but they're real challenges, and that is one of the key challenges that we need to be addressing and we are confronted with. And Carrie, Nargis?
Yeah, I totally agree, and Esther explained it very well. So the importance of system thinking and a holistic approach to that life cycle system, and the technology that we are leveraging, considering the carbon footprint, is a main element, and we see this ongoing discussion.
I think what a really important takeaway in this theme is that the data is never neutral. It's always designed. Somebody's asked about what data we are collecting and how we're analyzing that data. So I think we, as a society, need to move away from this concept that data is somehow a neutral resource, but it is always a design set. And so thinking about the system of systems and what data did we not collect, what are we not analyzing, what relationships have we not yet studied, are important, as important as the data we are collecting and the decisions we make with those data. Yeah. All right, other questions before we break? We're right kind of close to time, but we could squeeze in one more burning question. Yes.
This is a question for, I think, all three of you. Are you finding limitations, Mr. Cook, you brought up the challenges that you faced with collecting the data for your university. And also, are you running into problems in data collection and processing needs in your modeling? And so it's a question really for all of you, and and Esther also, how that affects the outcome of how you can predict things.
Yeah, thanks for the question. I think the data collection definitely that's one of the major component and the challenges, especially if you look at like when you scale up the digital twin, right, from a campus to a city, and how you're going to collect all this data and process them, right? And I'm also doing some research on a concept called edge computing. So that's the opposite to cloud computing, right? That's where you process the data closer to where it's generated, right? And that has, I think, a huge impact on a lot of things: the latency, the amount of data, and also privacy, right? Because you have processed the data where it's generated, so you don't store all the raw data. Yeah, I think that's a topic I think very important. Even though I don't have a a direct yes or no answer at this point.
For the next seminar.
Yeah, it was a great question, specifically when in the context of modeling or digital twinning, when we're looking at, we have access to many sources of data, but the problem of the lack of standardization around how we're collecting data, and that makes it really sometimes hard for merging and taking a good use of that data. It's a major aspect.
And then you throw in AI and machine learning that makes it.
Right.
Yep. And I'll just add, in addition to what they both said, the challenge we experienced, one of the challenges I experienced, maybe this was 4 or 5 years ago, was there's a lot of data that's being collected. Sometimes we don't know why we collect the data, and then we don't contextualize the data, so you have all this information, and it means nothing because it can't empower your decision making. So
The problem with that, retrieving that data and where it's is a problem with that also retrieving that data from where it was generated. I would think that would become a major problem to apply to a model.
yes. So part of it is retrieving the data, part of it is the data quality. So now you have to, and part of why DFW had to partner with NREL is recognizing that the skill set and the capabilities and the brain power, even though they have very smart people working there, you now have to look to different experts to come help you and contextualize that data and then clean it up. And then, they had a partner that came through and said, you could process the data on the edge. And that has meant a lot of benefit for like safety and security, because you need to contextualize that information fast. And you need to be able to predict, that I'm noticing people are gathering in this area. What is going on? And then I need to react because if you think, oh, I can just send an officer, what if the officer is, 3 minutes away? What does that mean in terms of security? You don't have the luxury. So you need that data contextualized fast. You need the access, and you need to be able to start pushing. You need the edge processing, of course, but you need the predictive analytics to start saying, okay, oh, these are people just gathering because they're trying to go to the restroom. And then we don't want that. So what technology can we deploy so that we don't have people gathering around an area just to go to the restroom? So it starts making you think, again, of the system, what small decisions, and the way DFW framed this was, little things make big things happen. So you're making little incremental steps of contextualizing that information as much as you can, and then that makes a difference in the bigger picture, and then you start getting a broader picture, and it just gets clearer and clearer with each step and each decision, but it's an intentional effort. And it's an effort ridden with challenges, but I think it's also exciting because we are actually seeing progress. Hopefully it answers your question.
Great question by all of you. Great answer by all of you. Thank you.
Great, thank you. All right, everyone, please help me thank our panel of presentations. I'm really glad to bring together this group because as I've been out in the world kind of looking for digital twin examples, and I found 3 awesome examples to share with you today. So it was exciting to bring all this work to the conference.